Hello everyone, my name is Du, and I come from the Structures Computer Interaction Lab at UCLA. Today, I'm going to show you a framework of autonomous coding with rollers based on vision and force control. Spray painting appeared multiple decades ago and has been widely used in vehicle factories. However, due to the main shortcomings such as the requirement of expensive equipment, high risk of uneven finish, and laborious cleanup of surfaces that are not expected to be spray painted, it is far from being commonly applied in daily life. In contrast, roller painting needs minimum preparation. Just a customizable roller and paint are enough. It can also cover small and tricky areas with better color consistency. But inhaling toxic fumes for days or even longer is detrimental to human health. Painting with rollers hours and hours will trigger sore backs, skin irritation, and headaches. In the past, several different painting platforms were built. As shown in A, an affordable and movable platform was developed, but the painting quality is often unsatisfactory. The robot in B mainly aims at human-robot collaboration and cannot locate the plane to be painted autonomously. The 3-degree freedom robot in C was designed for spray painting only on ceilings by moving vertically via a zigzag ladder, so its workspace is very limited. Peak robot in D is designed specifically to perform repetitive painting at high elevations on tall walls. In summary, there are several shortcomings of prior work. No force control, and painting of uniform thickness is not ensured. None of them are suitable for autonomous painting of 3D objects. When it comes to 3D autonomous painting, the main challenges include 3D shape recognition, hand-eye calibration, and autonomous path planning. This is our experiment setup. As you can see, we use a depth camera to generate the point cloud of the object. The large amount of point cloud data can be unnecessarily computationally expensive, so we downsample them to a voxel of size 0.1 cm. Due to variations in point densities in the point cloud and the measurement error of the depth camera, the sparse points that are far from others are outliers, and they may lead to errors in normal estimation. We remove these points. After this step, there are still irregularities because of the slight inaccuracy of the distance measurement of the depth camera and the invalid depth data for some points. As a result, we smooth the data through polynomial interpolation. The final point cloud after being processed is shown in A. A point and its neighbors constitute a surface, and the corresponding surface normal is estimated. Finally, we apply k-means clustering to classify how many planes the object has. Since k-means clustering takes the class number as input, we vary the class number and calculate the sum of squared errors, which is called inertia in B. It can be seen from B that there is a huge drop of inertia when the number of planes is 3, but not afterwards. Hence, the depth camera keeps 3 planes of the object in view and computes the respective normals of the planes. The point cloud is divided as shown in C according to the normals. Once the robot's eye sees how many planes there are on the 3D object and their dimensions and positions, the robot's hand needs to perform painting. Thus, the transformation from the coordinate system of the eye, denoted as C here, to the coordinate system of the hand, denoted as E here, needs to be done. The process is called hand-eye calibration. After that, we implement autonomous path planning. It mainly consists of 3 parts. First, we find the best plane to fit each cluster of points by minimizing the sum of square distance from each point to the corresponding constructed plane. D to F here are the 3 constructed planes by projection. The local coordinate system on each surface is defined by the surface normal as the z-axis, the x-axis randomly chosen within the surface, and the y-axis determined using the right-hand rule. The trajectory of the roller is then planned, and the maximum x-coordinate or y-coordinate difference is measured. The red rectangles in G to I are the roller trajectories. The width of the rectangle is the roller cover width, and the length of the rectangle is the range of x-coordinate or y-coordinate along the trajectory. The dashed black lines represent the movement direction of the roller. Overlaps between adjacent trajectories ensure complete painting. The robot needs to switch the roller from one painted surface to the next to be painted. Obstacle avoidance is necessary during switching for safety. We build the obstacle, i.e., the surfaces that have been painted already, by assembling the trajectories in MoveIt, and utilize OMPL for obstacle avoidance. Let me show you how the switching looks when the robot is working. All industrial robots, including Sawyer, the robot we use for experiments, are equipped with position control. Because of the error of depth measurements from the depth camera, a robot with pure position control is not able to maintain a constant force while painting. It's also unable to adapt to bumps or dents. Sawyer has torque sensors inside, from which forces in every direction can be obtained. The x-axis in this plot stands for the distance the robot moves along the object surface, while the y-axis is the force read from the embedded sensors in Sawyer. We can see that even though the robot started painting with an 8 Newton force, the force drifts a lot when the robotic arm moves under pure position control. To compensate for the drawbacks mentioned above, we designed a compliant roller handle and incorporated it with a cost-effective ultrasonic sensor. Before starting the experiments, we built a map from distance between the ultrasonic sensor and the surface, d, to force applied onto the surface, F. The distance d is the y-axis in the second figure, and the corresponding force F is the y-axis in the third figure, while x-axis is still the distance the robotic arm moves along the object surface. 1 is the microcontroller receiving the distance signal from the ultrasonic sensor and publishing it to the robotic system through ROS. 2 is the spring damper system. 3 is the roller cover. This method is similar to position feedback control, but precisely speaking, it's passive impedance control because it involves a compliant roller. This equation denotes the model the robot software uses to implement active impedance control. M is the positive definite diagonal inertia matrix, and K and D are diagonal matrices containing the robotic system control parameters related to spring stiffness and the damping coefficient of each joint. FEXT includes all the external forces from the environment, primarily composed of the reaction force from the target surface. Our design realized the force control by changing the compliance of the last joint, which is the second term, while the first and third terms are negligible. From the second figure, we can see that the distance variation when the robot paints with an 8 Newton force using passive impedance control is within 4 mm, 3% error in force correspondingly. Here is a summary of our overall control regime, where the position of the object is known as XD and the corresponding joint angles QD is calculated using inverse kinematics. The joint angles are controlled to be QM, which is not equal to QD due to control errors. When the robotic arm moves, the ultrasonic sensor monitors the distance from the surface to realize force control. If the ultrasonic reading changes unreasonably, it means that the roller is painting edges, in which case the embedded active impedance control is triggered. Otherwise, the passive impedance control leads the painting process. Coating thickness is related to the ability of a coating to protect coated surfaces, and thus is an effective metric to evaluate the painting quality. Here, we compare the performance of 3 painting strategies: human hand painting in the dashed yellow line, robotic painting with pure position control in the dashed green line, and robotic painting with passive impedance control proposed by us in the red line. The x-axis is the number of coating layers, and the y-axis is the coating thickness after being dried. Notice that the passive impedance control scheme has the same trend with human hand painting. With the increase of coating layers, the coating thickness increases continuously. The slope of robotic painting under passive impedance control is smaller than, but comparable to, human painting. In summary, we propose a low-cost autonomous painting framework that realizes performance close to human level according to the evaluation of painting quality. The framework is applicable generally to any domestic robotic arm. In the future, the robot can be improved in several ways. First, a wheeled pedestal should be added so that the robot can paint larger surfaces. Second, more cameras need to be attached to the robot for complete scanning of 3D objects. Sensor fusion will certainly be necessary in that case. Currently, the camera is fixed on the ground and its view is limited. Third, the robot can only paint flat and simple curved surfaces now, but not curved surfaces with continuously varying surface normal, like a sphere. This can be considered as a future direction. Finally, it would be cool if a robot can not only paint as well as humans, but also do online painting quality checks without human intervention. If you have any questions about our work, please feel free to contact me. Thank you for your time.